All right, hello, folks, and welcome to another one of our interview video series where we interview geologists with backgrounds, their past, get to know them a little bit. Today, we're going to be talking with Dr. Carey, who is an emeritus professor of oceanography at Island. Talk a little bit about his career path, how he got into geology, the work he's done through his career, and then maybe share some of those lessons I wish he would have known when he was marking on the journey that he. Again, Stephen, for joining us.
Well, thanks, Shawn. It's really nice to meet you. I enjoyed the content on all your shows.
Oh, thank you so much. Yeah, so full transparency, Steve and I don't know each other. This is we actually met sort of. We've exchanged some emails when I was trying to report on some of this earthquake swarm that was on there and some geologic activity. He commented and obviously knew more about that region, having to knew, and so very valuable source of information. I knew he would be a really interesting person to know. So, Stephen, let's just get right into background, how you kind of came into geology.
Yeah, so I grew up in a small town in Western Massachusetts. Greenfield, Massachusetts was where I was brought up in a population of about 15, 20,000 people. And I think as most geologists will tell you, from a very early age, I just loved being outdoors. And we used to go off in the woods and wander and hike up mountains and look at rocks. And I was just fascinated by the landscapes and all curious about how mountains formed and what rivers did. But at that time, I think I also developed a really keen interest in science. And so I'm going to date myself now. When I was in middle school and high school, that was like the mid 60s to the early 70s. So my interest in science, I think, was determined a lot by the time frame that I grew up in. This was the height of the space race,
Yeah.
okay? Racing to put man on the moon. Science was just absolutely fascinating to me at that time. I was into electronics. I was building my own amateur radio gear at the time. And of course, I was into rockets, much to the chagrin of my parents. So we used to make batches of solid fuel rocket in the basement on scrap pieces of wood. And one day my dad went down looking for some pieces of wood for our fireplace, picked up one of these test strips of rocket fuel,
Oh no.
unbeknownst to him, brought it up to the family fireplace, put it in, and of course, the fuel ignited, spraying sparks all over the carpet. And that was the end of my future career as a rocket scientist.
Before it even got off the ground, right?
Before it even got off the ground. Then I think in my senior year in high school, we had a student at Greenfield High, very smart guy, had gone on to MIT and got his PhD in geology. He came back to our physics class and gave one of these little lectures about, what's it like to be a geologist? Like, firefighters come into class and
Yeah.
you have a question and answer. And I remember sitting there and I'm thinking, boy, I can have a career in science and I can be working outside. And I thought, where do I sign up?
Yeah.
Right? Love the outdoors. I love the thought of having science integrated with working outdoors. So I decided, my senior year, trying to decide, like the student you were describing, what are you going to go into in undergraduate? So I went to the University of Massachusetts in Amherst for my undergraduate degree in geology. And I kind of knew right away that I wanted to go into geology. So I declared it as a major very early on. And again, my experience as an undergrad, I think, was very much influenced by the time frame of that period. So I was an undergraduate in the early 70s. So you know what was going on in the early 70s? Earth
Right.
sciences was undergoing a major paradigm
Yeah.
change
Yeah,
in
exactly.
plate tectonics.
Right.
We were right in the middle of it. And the students could tell it was a very exciting time. And there was, I think I describe it as a bit of tension. When science goes through paradigm changes, there's always tension between shifting from one paradigm to the next. I think some of the older members of the department were not quite convinced about plate tectonics.
Right.
Some were.
Upended their apple cart for sure. Yeah.
Yeah, and plate tectonics was, I mean, it was just starting to be integrated into the textbooks. So we knew about plate tectonics. And one of the things that I realized at that time was that a lot of the major pieces that fed into the plate tectonics paradigm were coming from observations in the ocean. So magnetic lineations on the seafloor that illustrated spreading at the mid-ocean ridges, the discovery of deep sea trenches, where subduction was taking place, oceanic volcanism and hotspots. So it was kind of clear that a lot of the interesting things that were happening at that time in plate tectonics were related to the field of marine geology. And so when I was able to get most of my undergraduate courses out of the way very quickly because I declared my major early on. So by my senior year, I was taking graduate courses in geology at the university. And I took a course in marine geology. And it seemed like a really perfect fit because I always had a love for the ocean and an interest in the ocean. My family we used to vacation at the seashore all the time. I became a scuba diver when I was in high school. The ocean was this kind of big, mysterious thing.
Right.
And it was fascinating to me that all of these interesting discoveries about plate tectonics were happening in the ocean. So I thought, okay, here I am, I'm a geologist. I want to continue on and I want to go into marine geology. So I enrolled at the Graduate School of Oceanography at the University of Rhode Island. And that's where I did my graduate work for master's and then PhD.
Mm-hmm.
So that's the kind of path that I took to arrive at marine geology specifically. But
Right.
as I mentioned, a lot of what happened was kind of being in the right place. My interest in science was driven by the space race. Interest in plate tectonics was happening right when the paradigm shift was going on. So that was kind of how I ended up on that route to marine geology.
And what specific aspects of marine geology were you kind of focused on in in your graduate studies?
Yeah, so in graduate school, I linked up when I went to interview. I met someone that I felt I'd be really interested in working. That was Haraldur Sigurdsson, and Haraldur he was a phenomenal field
From
geologist
Iceland, right? Yeah.
from Iceland, very well known volcanologist. And before Haraldur came to URI, he had worked in the West Indies in the Lesser Antilles subduction zone. And he was interested in reconstructing the history of explosive volcanism by looking at volcanic ash layers in sediments on the deep sea floor around the Arctic. So one of the projects I got involved with kind of early on in my graduate studies was a series of oceanographic cruises that collected deep sea cores, and then we split the cores. We found the ash layers in the cores, and we used electron microprobe analysis of the glass shards to kind of chemically fingerprint the
Mm-hmm.
layers to different volcanoes.
Right.
So,
Matching them up to their sources. Yeah.
yeah, they're source volcanoes. And then using biostratigraphy, you could kind of get an estimate of the age. So the cores provided a way to kind of build up a history of explosive volcanism in a particular region. So that was what I kind of focused on mostly during my early part of my graduate career.
Can we talk a little bit about, because the ocean, I grew up in the Western US, landlocked. Like the ocean is definitely not just mysterious to someone like me, but like maybe a little bit scary and not what I would think of first when I think about geology and finding data. So maybe talk a little bit about how different it is working in that marine environment when you're trying to collect data versus those of us on land that are out mapping and hiking up hills and stuff. Like what are some of the drawbacks or maybe some of the positives?
Yeah, well, interesting question. So the particular studies that we were involved in to collect sediment cores is different than field geology because it's a major operation. You have to get a ship, you have to get the coring equipment, you need sonar to locate the areas where you might do your coring. So it's not like you can just walk to the site and do
Yeah,
it.
much more
It's a very,
challenging.
yeah, it's a very expensive proposition. And actually, that makes the samples that you collect during oceanographic research are incredibly valuable because you expend so much money to collect them. So you cherish them once you get them.
Right.
And it's interesting you ask this question because I look at the beginning of my career when I did early work in the ocean and the latter part of my career, the technology just completely changed. When we used to go out early on in oceanographic ships, we had paper maps. I mean,
Right.
you really
Trying to locate
barely,
yourself. Yeah.
yeah, there was no satellite navigation. You barely knew what the bottom of the ocean looked like. You could use a depth finder to kind of do a profile so you knew roughly what it looked like. Nowadays, we have multi-beam sonar, which produces a 3D image of the seafloor with centimeter scale resolution. I mean, it's amazing how technology development has transformed research in the ocean.
Yeah.
I'd say the early days were very adventurous and was kind of poke poke at the elephant and try to
Right.
figure out what it was.
A shot in the dark kind of thing.
Out in the dark,
Yeah.
exactly. I mean, lots of times we would send the core down and the core would come back on ship and it'd be bent in half.
Wow.
You hit a rock outcrop or something.
Oh yeah.
Yeah.
So how when you're collecting the ash samples on the seafloor, do you need an eruption of a certain size? I'm just sort of trying to visualize that ash hitting the surface of the ocean and then starting to settle out, drifting to the bottom. There's currents when it gets to the sea. Like how pristine are those samples, and does it take a certain size of eruption really to even leave that kind of record?
Yeah, that's exactly right. Only the largest eruptions are really recorded in the deep sea sediments, principally because of the process of bioturbation.
Yeah.
So in the deep sea, when you settle, if you have a very thin ash flare from, say, a very small eruption, the biological, there are worms and all sorts of critters that live in the deep sea sediments, and they churn it all up. It's like the earthworms in your yard,
Yeah.
basically. So the thin ash layer won't be preserved very well. It'll be redistributed in the sediment.
It'll be mixed in with seafloor sediments that were already
Uh,
there, but you
yeah.
still have enough
And
ash there. You can find the glass shards, and yeah.
sometimes you can.
Okay.
We really focused on the major layers that you could see. They end up as white bands in the deep sea sediments. Those are from very large eruptions, very, very big explosive eruptions that generate, cubic kilometers of magma, widespread dispersal, hundreds of kilometers away from their source.
Right.
So that's a good point. The sort of record that you built up is filtered to some extent, in that you're only looking at the very large eruptions.
Right. Yeah. So it's probably hard to quantify. Like, all you want to really see is there is a record of the ash. You can date the ash. Hopefully, you can use the geochemistry to trace it back to its source, and that gives you an idea of dispersal of that eruption, like how wide it was.
Yeah.
So how did tell me about the rest of your career once you kind of finished up your graduate work? What was the next stage kind of in your early career? What was next for you?
Yeah, well, I think, lots of people's careers are defined by signposts along the way and certain events. And I think one of the biggest events that influenced my career from when I was in graduate school till the very end was the eruption of Mount St. Helens. So that happened in May 18th, 1980. It is the 45th anniversary of the eruption this year.
True.
It
Yeah.
is hard to believe.
Yeah.
Um, so we had been working on ash layers in the deep sea cores. And when Mount St. Helens erupted, most of the volcanic ash fallout from Mount St. Helens happened on land. And so we thought, well, we've been looking at these ash layers in the cores, but we've really never seen a nice land-based analog of an eruption that occurs where you know the size of the eruption, you know the wind pattern, you know the area, and you know the characteristics of the layer. So we wrote a rapid response proposal to NSF. They funded it. We packed our bags. 1 week after the May 18th eruption, we were in the field at Mount St. Helens
Wow.
looking at the ashfall deposit. And I can tell you that my aha moment in terms of wanting to study volcanoes happened when I was standing in the blast zone 1 week after the eruption of Mount St. Helens. The landscape was completely devoid of life, ashen gray. There were Douglas fir trees that were 1 meter in diameter that were mowed down like matchsticks. It looked like someone took a giant comb and just ran it through the forest. I stood there, it was surreal. I stood there and I said, this must be what it's like to be at ground zero from a nuclear blast.
Right. Just the power.
And
Yeah.
the energy, I mean, you could almost feel the energy. And I thought to myself, I want to understand what causes volcanoes to behave like this? What are the hazards associated with them? And so that really kind of drove my interest in explosive volcanism. I mean, I'm a volcanologist, but I really specialize in explosive volcanism.
Mm-hmm.
That's really where it started.
So you go on, this is during grad school, right?
During
1980?
grad school. And in fact, a big part of my thesis, which was kind of ironic, a big part of my thesis was about Mount St. Helens. Even though I got my degree in marine geology, here, a big part of my thesis was a land-based volcano,
Right.
that none of which went in the ocean.
Yeah. So maybe talk for a second about how different, a lot of people know a lot of things about the 1980 eruption at St. Helens. But talk a little bit about how a land-based eruption like that, which is the one we're most familiar with and the ones we tend to, learn from, how that differs from a submarine eruption of a similar volcano and of a similar size. Like, what are some of the eruption dynamic differences between those two?
Yeah, that's an interesting question. So we know a lot about the dynamics of land-based explosive eruptions from computer simulations, laboratory experiments. In the ocean, of course, you have this enormous overlying water. And when you have an explosive eruption, gases in the magma expand and fragment the magma into small pieces. So when that happens on land, the fragmented mixture of gases and particles goes up into the atmosphere. And it behaves in various ways. Some of the stuff falls out, some of it collapses to form pyroclastic flows and surges. In the ocean, we don't really there's certainly explosive eruptions that occur in the ocean. We don't understand the dynamics of that very well because of the complications of water. So what happens when you interact water with magma, it often turns to steam. And so the fluid dynamics of submarine eruption column that has volatiles that are being released from the magma, but then seawater that's turned to steam, those dynamics are incredibly complicated, not only from a physical, but a thermodynamic standpoint. So the water that's vaporized can recondense, and that can affect the behavior of the eruption column. The settling of the particles in water is very different. Sometimes they float, sometimes they sink, depending on the density. So my opinion, the next big leap in the field of volcanology is going to come from understanding the modeling and experiments related to the dynamics of submarine eruptions. It's like an open frontier, basically.
Right. And we have very few analogs, right? I mean, there was the 2022 Hunga Tonga one.
Yeah.
And, then it's like like Krakatoa. I can't even remember. Like there's not that many, right?
And I mean, so there are eruptions that are hybrids, that they start submarine, but they breach the ocean and go up into the atmosphere.
Right.
That's what Hunka Tonga did, and that's what Krakatoa did. But there are some eruptions that are highly explosive eruptions that are completely submarine.
Hmm.
They never break the surface. So it's a really fascinating field, and it's kind of the one that I've kind of ended my career looking at kind of wholly submarine explosive volcanism.
Yeah. Yeah, well, let's maybe stay there for a minute. We might have to go back to the middle of your career later, but
Yeah.
I think it feels like a good segue to talk about what was going on in the Aegean Sea, and what's happened in the Aegean Sea with this island north of, or a seamount, I guess, an underwater volcano north of Santorini called Kolumbo. If you want to maybe introduce that to the viewers,
Yeah.
that'd be great.
So Kolumbo is, well, the whole Santorini volcanic system includes volcanoes that extend in a lineament from southwest to the northeast. Santorini is the main volcano, subaerial volcano there. There's a whole series of submarine volcanoes along that lineament, which is a very tectonically active region. We did some exploring with remotely operated vehicles. So these are robot vehicles that you send down from a ship. They have high definition cameras on them. They have sampling arms, so you can collect samples, and they get their power from the surface. So it's a really neat exploration tool. It's not like a submersible. No one goes down in an ROV. You pilot it from the ship. So they can stay down indefinitely. And we used ROVs to explore Kolumbo volcano. We were interested in Kolumbo because, let's see, it erupted in the 1600s. And even though it was getting back to our discussion earlier, is a wholly submarine volcano. But in the 1600s, when it erupted, it breached the surface. It caused a tsunami on the coast of Santorini. There were a number of people that were killed, probably by pyroclastic surges and gases that were discharged. So we were interested in looking at that volcano. How is it different from Santorini? Was it a different magmatic system? What kinds of eruptions were occurring there? So we've had a couple of expeditions to Kolumbo. And one of the surprises that we found, so it has a crater. It's about 500 meters deep. It's got a diameter of several kilometers. When we first went there, sent the ROVs down, on the bottom of Kolumbo volcano, we discovered this incredible hydrothermal system.
Hmm.
It's hot vents, and there was a massive sulfide deposit being formed inside the crater of Kolumbo. These are really fascinating deposits because these are the kind that are rich in gold and copper, not like ones that are mid-ocean ridges.
Right.
Because the magmas that are being produced at Kolumbo were rhyolites, so they're high silica magmas.
Yes.
So the fluids that are percolating through these high silica arc magmas, they generate hydrothermal fluids and mineralization, which is different from mid-ocean ridges. These are the kind of deposits that mining companies are now looking at in the Western Pacific to exploit. And there was one in Kolumbo. So Kolumbo was interesting as it has an active hydrothermal system. And then seismic work at Kolumbo showed that there's evidence for a magma chamber still underneath Kolumbo.
So that still has at least a partially molten mass.
Exactly.
And how deep is Kolumbo below the surface of the ocean? Like how much water is sitting on top of it?
Yeah, well, the highest point on the Kolumbo rim is only 18 meters below the surface.
Oh, so it's really close to the surface. Wow.
Sure, but that's only on one part of the rim. The rest of the rim is about 100 to 200 meters deep.
Okay, but still pretty shallow.
So very
like,
shallow.
Yeah, not like
Very
thousands
shallow.
of feet, right?
So the concern was if Kolumbo becomes active again, there are hazards, there are tsunami hazards, there are hazards with volcanic ash fallout. And then I think there's also hazards associated with the discharge of that hydrothermal system.
Right.
So these hydrothermal systems are rich in arsenic and mercury,
Yeah,
so
toxic materials, right?
toxic material. So when that seismic crisis occurred, people were obviously, and for good reason, concerned that maybe something at Kolumbo is being reactivated and there's potential for future eruption at Kolumbo. But I think, as you showed in some of your shows, most of the seismicity was not around Kolumbo. It was more to the northeast in the Amorgus Basin.
Right, on the fault systems and
On the faults.
yeah, the earthquakes kind of bared out. I thought that it looked more like a linear fault
Yeah,
structural, control there.
yeah. But there's been some, I mean, there's a lot of seismic work that was done there by Emily Hooft at Oregon,
Hmm.
and her students have now shown, they looked at some deep seismic profiles, and it looks like much of the seismicity could be associated with magma movement, but not magma that was underneath the volcanoes. It was
Right.
sort of translational movement of magma that was accommodated in this fault zone, so it triggered earthquakes, but it didn't lead to an eruption at any particular fixed point.
What are there? Does the Greek government have different types of monitoring equipment or other entities as well? Like, how are they monitoring Colombo as a volcanic hazard? Is there GPS that works on the seafloor to see if it's actually uplifting, or there's tilt meters or something?
They did deploy some instruments, but a lot of the seismicity was determined by the local seismic stations. But my colleague and good friend, Evi Nomenkou, who's at the University of Athens, she has been spearheading the development of a submarine monitoring station at Colombo.
Hmm.
Where it deployed temperature sensors, seismicity, and some of that equipment wasn't in place at the time of the seismic crisis, but they're looking to develop real-time monitoring of Kolumbo volcano with instruments deployed directly on the volcano.
Would that be the first one of its type, or do we have something like that already in place somewhere else in the world, like a submarine volcanic
Oh yeah,
monitoring
well
system?
there's cabled networks that are off the west coast of the United States that have been monitoring things like axial
Oh
volcano.
yeah, that's right. Okay.
Yeah. So those exist. Not so much in arc volcanoes, I would say. A lot of the
Mhm.
work has been on mid-ocean ridge volcanoes,
Yeah, the more passive ones. Yeah.
more passive ones, yeah. Um, but those, of course, they don't pose as much hazard, obviously, because the
Hmm.
eruptions are generally lava flows and pillow lavas, and they're very deep water.
Yeah, yeah, not nearly the same level of gas concentrations and explosiveness as something like that.
Not at all. Yeah.
Interesting. Yeah. So did your work at Colombo, was it focused on that, or did you sort of get looped into that through something else? I almost feel like in talking to you and in the correspondence we've had, like you ended up getting associated and working with the Colombo volcano, or was that your primary focus?
Um, well, we had started on Kolumbo way back in 2010.
Okay.
We kind of had a long history of looking at the volcano, and we had really focused on the eruption that occurred in the 1600s to try to understand the type of magma that was erupted, how much gas was in the magma, and what was the mechanism for the generation of the tsunamis.
Yeah.
How did Kolumbo volcano generate tsunamis that impacted the coast of Santorini? And some of the seismic work that we did, or that there was a group in Germany that's done a lot of really excellent seismic work. And we think now that the tsunamis at Kolumbo were associated with collapse. So the Kolumbo cone during the 1600 built up. It was a pumice cone, basically, that
Mm.
built up over time, very unstable. And parts of it collapsed. And you can see the evidence for that in the multi-beam bathymetry and the seismics. And that collapse, we think, is what triggered the tsunamis.
Oh, so it wasn't actually an eruption, and the displacement of water from the eruption was actually
Well, it's
displacing
probably,
water through that collapse.
yeah. And that, volcanic island collapse is really one of the major mechanisms for generating tsunamis around the world. Um, here on the east coast of the US, we actually have a tsunami threat from the collapse of volcanic islands in the Canary Islands.
Right, La Palma, yeah.
Yeah, so there have been these mega collapses that occur at oceanic islands that generate huge tsunamis that can go all the way across ocean basins and impact very distal coastlines.
Yeah, so this one with Kolumbo and the tsunami it generated, do you see evidence for that tsunami throughout the Mediterranean? Like in all parts of the Mediterranean, do you see that? Or was it much more localized and kind of just hit neighboring islands?
It was much more localized. And, a lot of the imprints of tsunamis that occurred in the past are based on tsunami deposits that you can find in coastal areas. And there's been kind of dubious evidence about whether there's a tsunami deposit from the Kolumbo eruption on Santorini. They're very difficult to tell from storm deposits and other kinds of Newark deposits. Around the Mediterranean, however, there is evidence for a mega tsunami associated with the Minoan eruption of Santorini, the caldera forming eruption.
Right. Which makes sense because that was so much bigger, yeah.
Much bigger, yeah. And there's lots of evidence from distal, all the way to Israel, that have been found tsunami deposit in the Nile Delta.
And when we mentioned, sorry to interrupt, but when you mention tsunami deposits, the vision I always have, and correct me if I'm wrong, is basically a tsunami would transport shoreline deposits, sands and stuff, well-rounded, constantly worked, up to some higher elevation where you'd expect to have more just colluvium and broken angular fragments. Is that pretty much more or less kind of the smoking gun and the evidence for that?
That's exactly right. But the key piece of evidence that is used to kind of discriminate tsunami deposits from storm deposits is that tsunami deposits often contain displaced oceanic microfossils. So sediment that's ripped up from the seafloor gets incorporated into the tsunami that washes onshore. It, incorporates debris from the shore, but it also has a component of the offshore sediment.
Right, because it's this big pulse of water moving through the whole water column. And then, so it's picking that stuff up, taking it with that tsunami, and then transporting it up onto higher elevations. Interesting.
This study of tsunami deposits is really quite fascinating.
Yeah. Yeah, well, obviously, everyone, in the Santorini one, I think that's why this event earlier this year was in the news so much, is it happened to be close to this very well-known, not just tourist destination, but known site of one of these, quote unquote, super volcanic eruptions. And so people just put the two together and ran with it. Yeah. And that's where I was trying to provide a little bit of balance to the discussion. Like, wait, we're not even seeing the earthquakes anywhere near Santorini. And
I agree. I was very concerned watching a lot of the coverage on YouTube and other channels, highly sensationalized coverage about, what can happen, a mixing of facts and speculations, and it's very dangerous.
Yeah.
It can have economic impacts for the people of Santorini, for example.
And it did have impacts there. The tourism industry suffered.
Absolutely.
Yeah.
Yeah.
Interesting. Well, let's go, we kind of went from the beginning to the end of your career, so let's maybe circle back to the middle. Any other kind of highlights? Obviously, you've had a very varied and interesting career, and I don't want you to necessarily feel like you have to regurgitate all of that, but maybe some of the variety or some of the highlights in your career. Have you always been studying submarine volcanoes? Has that always been sort of the common theme?
No, this is kind of where my career, I always say I had kind of have 1 foot on land and 1 foot in the ocean. I'd say back in the 80s and early 90s, I was focused mostly on land-based volcanoes.
Okay.
So we studied Mount St. Helens. We studied El Chichon volcano in Mexico. We did a lot of work at Vesuvius in the 79 AD eruption of Vesuvius. We worked at Tambora volcano. We worked at Krakatoa volcano. So a lot of the middle part of my career was really kind of land-based. volcanoes.
And mainly looking at, like, what was the main focus? Was it looking at the dispersal of the pyroclastic material, or like quantifying the size, or?
Yeah. So my approach in the 70s, I'm going to make this point, in the 70s and the 80s, the field of volcanology was really going through a transformation as well. So early on, volcanology was kind of an observational science, I think, mostly. And in the 70s and 80s, there was a big push to quantify the processes of volcanic eruptions. So kind of the field of physical volcanology
Yep.
came into its own. There was an application of physics, fluid dynamics, laboratory experiments to better understand the behavior of, in particular, explosive volcanism. So on the one hand, I became very interested in that. But on the other hand, I still was very interested in doing field work. So I was very interested I didn't want to sit in front of a computer all day and model eruptions.
Right.
I love being in the field. So I was looking for ways to marry modeling of volcanic eruptions and understanding the physics of volcanic eruptions with then how do you read that in the deposits?
Yeah.
Volcanic eruptions.
Right. The direct observations versus the modeling. Right.
Exactly.
Yeah.
And so I think one of my most cited papers is a model that Steve Sparks and I developed. We were interested in developing a model for big eruption columns, mushroom clouds that develop over large-scale explosive eruptions, like at Mount St. Helens, for example. We were interested in looking at how are particles transported up into the atmosphere? Where do they fall out once they settle back to the ground? So we developed a model that predicted the dispersal of particles of various size as a function of eruption column height and wind field. And so this is what I like to call forensic volcanology, really. This was a method that you could use. You could go out in the field and you could measure the size of particles from a fallout deposit. And you could use the model to reconstruct, okay, I've got this fallout deposit. How big was the eruption?
Right.
You could reconstruct the height of the eruption column. And because it relied on convective plume theory, the physics for that, it's the same for an industrial smokestack, a forest fire, a volcanic eruption.
Yeah, same dynamics, right?
Physics are all the same. So it was based on a physical model. And what the nice thing about Mount St. Helens, for example, is we developed a model and we say, well, does this thing actually work? You can build all the models you want.
You got to ground truth it somehow.
Yeah, you got to ground truth it. Mount St. Helens was perfect. The height of the eruption column was measured by radar. The wind field was measured. We knew everything about the eruption. We measured the parameters of the fallout, and the model worked. And so we had this model in hand, and we were kind of poised. And so this was a model of things called a Plinian eruption.
Yeah. Very explosive. Yeah.
Very explosive. And Pliny, the term Plinian was named in honor of Pliny the Younger, who provided the first historical description of an eruption.
With Vesuvius, right?
And Vesuvius.
Yeah.
So we thought, we have this model of Plinian eruptions. Where is the natural place to go? Let's go to Vesuvius and look at Pompeii and Herculaneum. That experience, I think, was one of the most exciting and satisfying eruptions that I've studied. Because you had this mix of archaeology and volcanology together in a very unique and interesting way. Have you been to Pompeii?
No, I haven't yet, but I'd love to.
You have to go there.
Yeah.
I mean, it's just amazing. So we had unprecedented access to the excavation. And the goal there, both the cities of Pompeii and Herculaneum were both entombed in volcanic ash in one day. And the goal of our study was to try to take the deposits that buried Pompeii and Herculaneum, use the models to reconstruct what exactly was the 79 AD eruption like?
Yeah.
What processes took place? How big was the eruption column? How fast was the magma erupted? And we could determine all that from field studies of the deposits. So we spent a lot of time in the excavations, digging holes. They let us dig holes there, which was amazing.
Yeah.
Archaeological excavation.
No red tape.
And we were able to do it. And
Yeah.
beautiful stratigraphy of the volcanic deposits, of fallout, pyroclastic surges, pyroclastic flows. And that stratigraphy basically told the story of what happened in Pompeii versus what happened in Herculaneum. And the interesting thing about the results was that what happened in Pompeii and Herculaneum was really completely different. So at Pompeii, the city was initially buried by about 2 meters of pumice fall.
So just material falling out of the sky. And Pompeii's further away from Vesuvius, right? Just to kind of give us
It's
context.
further away, but the key thing was that Pompeii is to the east-southeast of Vesuvius. Herculaneum is almost due south, and the winds was blowing from the west to the east. So Pompeii was right downwind of the fallout from the eruption of Vesuvius.
2 meters of ash and pumice. Wow.
Pumice. And it's interesting because and we could tell from the model that this probably occurred over the span of several hours, at least. So we think a lot of people at Pompeii probably left the city during that time because that wouldn't have been lethal. You'd have pumice about the size of a pea or a golf ball falling on your head, but it wouldn't kill you. Then, during the night of the eruption of Vesuvius, the style of the eruption changed fundamentally. And instead of fallout occurring, parts of the eruption column collapsed and formed pyroclastic surges and flows. Those surges reached the city of Pompeii late in the night or early in the morning. That's what was lethal. So the people who had stayed in Pompeii were killed by pyroclastic surges.
Right. And just that hot, what was some of your modeled temperatures and speeds for that pyroclastic flow?
Well, the model was only for fallout. The model didn't model the flows. But we know that the speeds of pyroclastic flows and surges are in excess of 100 miles an hour.
Yeah.
And you could tell that the wood at Pompeii was carbonized. So you know that they were hot.
Yeah, right. And it incinerated those people, basically. Yeah. Basically. Right.
No escaping. And in Pompeii, when they excavated it, that's where they found the bodies.
Right. Because they were these cavities of weird shapes that were actually, because the way I explain it is their skin was basically, their bodies were probably vaporized, but the ash cooled up against their skin, created a harder layer of part of the ash there, and that it was in the shape of their bodies.
So I think what happened was, so the people were killed by the surges and they were buried by the surge deposit. But the cavity was actually produced by the decomposition of the body's soft parts.
Oh, okay. That makes, yeah.
So skin was not really vaporized.
Okay.
And we know from historic eruptions where people have been caught in pyroclastic flows that they're just badly burned.
Okay. Yeah, it's good correction. Thanks.
Yeah, good. The skin stays intact. But over time, the soft parts decompose.
Decompose, yeah.
Skeleton remains, but then you've got a gap in the deposit between the soft parts of the body and the skeleton.
So they did have bones in those cavities still preserved? Okay, that's something I didn't know either.
Yeah. So when they were excavating the deposits, there was this archaeologist, Fiorini, who came up with this clever idea. And he said, oh, wait, stop digging. There's cavities here. Let's pour plaster into the cavity and see what we find. And it was incredible. You captured the cast of these peoples in their final moments of life.
Yeah.
Sometimes the imprint of the clothing is on the cast as well.
Wow.
When we were working at Vesuvius, I was able to go inside one of the displays with the plaster cast of the body And it was a very eerie experience, I'll tell you.
Imagine, yeah. So how were things different at Herculaneum? If that was sort of the
Yeah,
sequence of events in Pompeii, tell me about
very
Herculaneum.
interested. You go to Herculaneum, completely different stratigraphy. There's no fall out there.
Because they're not downwind.
They're not downwind. So the first thing that hit Herculaneum were pyroclastic surges and flows.
Mm.
People in Herculaneum, they probably looked up at Vesuvius for hours and hours. They saw this big eruption column. There was lightning. There was seismic activity. It was all dark, but nothing was happening at Herculaneum.
So they stuck around longer.
Well, we think they were scared.
Right.
Because most of the bodies of Herculaneum were found in these boat chambers down by where the seashore was.
Like they were huddled in, like kind of hiding, if you will.
They were huddled. I mean, that was a macabre scene when we were there in the 80s when they first discovered these boat chambers. Inside these boat chambers were hundreds of people, skeletons just piled up. We think they were waiting in those boat chambers to escape by boats.
Yeah, they were just shuttling people off the
Yeah.
out of the area. Yeah.
And it didn't happen. And the pyroclastic flows and surges came, and instantly it was lethal for everyone in Herculaneum.
Wow.
So very different, very different processes.
Yeah, like different.
Depending on where the cities were relative to the volcano.
Interesting. Well, that's great. I mean, that has a lot to, my very limited knowledge of that very historic eruption.
Yeah.
Fascinating. Wow. Well, let's a couple more minutes, if you wouldn't mind, Stephen. Maybe I feel like we could dive into so many parts of your career and all these volcanoes and such, which are fascinating. But maybe let's wrap up with, how about some advice or things you've learned, lessons learned throughout your career that you might impart to someone majoring in geology today, or someone kind of just learning geology? What are some takeaways that you've learned?
I think the key thing for me was a very young interest in science. I think students can tell, or should be able to tell, at a relatively early age whether a path in science is something for them. And nowadays, it's literally so easy to explore what different fields are like, with all the resources on the internet, with interviews like this,
Right.
people who have careers in geology. The resources are just tremendous. And I would just encourage people to take advantage of these kinds of resources. If you have an interest, if you have an interest in a particular field, find a local college or university, show up at a prof's door and ask them, what do you do?
Right.
Is it something that I might like to do? During my career at URI, I often had students come and ask me, what is it like to be a volcanologist, or what is it like to be a geologist? But I think it takes initiative. You can't sit back and expect it to be handed to you. I think throughout my career, I found that there's a famous, line by Woody Allen. 90% of life is just showing up, right? You have to show up.
Yep.
You got to do the work. You got to put the hours in. You can't expect it to kind of come to you.
Yeah, I think I tell students the same thing. Got to be active. Got to be persistent.
Yeah, got to be.
Don't worry about annoying someone. If you're annoying, they'll tell you. But better to bug the person too many times to get what you're trying to get than not enough. So,
I think in general, people love to talk about things that they love to do.
Yeah, sure. That's ultimately what we're all doing here, is just sharing, right? Like just our passions and what we enjoy.
And there's another thing that students, I find in my years of undergraduate teaching, I found that students are reluctant to ask questions in class because they think it's going to be a stupid question.
Yeah, the social pressures.
Yeah, and I try to tell them there are no stupid questions. Don't worry about it.
Right.
Stand up and ask. There's a great Will Rogers saying, everyone's ignorant just on different topics. Right?
It's true. Yep.
So, yeah, make your voice heard.
Right.
Ask questions. Don't be shy.
No, that's solid advice. Great advice. So, well, hey, thanks again so much, Stephen. I feel like we could do a couple more hours of this because you have just such a wealth of knowledge and so much information. And maybe we'll do another one at some point in the future. But want to just appreciate you educating me on Santorini when all that was going on. That was very helpful. And even here today, a little bit more knowledge in my head now for about Vesuvius and that eruption. So thanks again for your time. We really appreciate it.
You're welcome. It was great to be here with you, Shawn.
Thanks.